In this lecture, we are going to talk about dislocations. So, they are actually line imperfections. In the previous lecture, we talked about point imperfections. In this lecture, we are going to talk about line imperfections. So, they are usually called dislocations. So, what is a dislocation? A dislocation is a line imperfection in a crystalline material. So, there are two types. One is called screw dislocation, a dislocation produced by skewing a crystal so that one atomic plane produces a spiral ramp about the dislocation. The second type of dislocation is called edge dislocation, a dislocation introduced into the crystal by adding an extra half plane of atoms. The third type is called mixed dislocation. It's actually the combination of the screw and edge dislocation. What is slip? Slip is actually deformation of a metallic material by the moment of dislocation through the crystal. So slip is actually the moment of dislocation in metallic material. So if you look at this figure, so in A you see a perfect crystal, right? In B, the crystal is cut and sheared one atom spacing in B and C. The line along which shearing occurs is a screw dislocation, right? A Berger vector B is required to close a loop of equal atom spacing around the screw dislocation. So what happens is that if you want to shear this perfect crystal about this plane, so you're going to end up with this figure. And if you try to close this deformation or this ramp in a loop, so for example, if we start from here and we go 1 2 3 4 planes or atom spacings in this direction, and then we go 4 atom spacings in this direction, and then we comes back 4 atom spacing in this direction, and we go in this direction by 4 atom spacing. So what we are going to end up with is an open loop. So in order to close this loop from here to here, so we call it a Berger vector. So a Berger vector is required to close this loop. Otherwise, if you continue with this loop, you are going to end up with a spiral loop. So this is a screw dislocation. It's a kind of a pizza. If you want to take out a slice out of the pizza, so this, what you are going to do is you are going to put a shearing force on the plane of the pizza, and a screw dislocation will form. So the second type of dislocation is called edge dislocation. So this is a perfect crystal, and what you do is you cut this, and an extra plane of atoms, this is an extra plane of atoms which is being inserted inside this crystal, and this extra plane is actually half. It's not full, right? It is half. If you look at this plane and this plane, so this plane is half of this plane. The bottom edge of the extra plane is an edge dislocation, and this is the bottom plane of this extra plane, so we call it edge dislocation, right? So if you form the same loop around this edge dislocation, if you go equal atom spacing in all the direction and try to close this loop, you are going to end up with an open loop, and in order to close this loop you need a Berger vector. Now if you look at the direction of the Berger vector, so the direction of the Berger vector is in this direction, whereas the edge dislocation is in this direction. So they are both perpendicular. So Berger vector is perpendicular to edge dislocation, right? Whereas the Berger vector here is parallel to the screw dislocation. So Berger vector is parallel to the screw dislocation. Let's call it SD. Okay, so if you look at this picture, so this is that extra half plane, right? So this is a edge dislocation, right? This is edge dislocation. Okay, so mixed dislocation actually contains both part of screw dislocation and edge dislocation, right? So here it's a screw dislocation, here it's a edge dislocation. Okay, if you look at this figure, in figure A, schematic of slip line, slip plane and slip Berger vectors. For A, this is edge dislocation, right? And B for screw dislocation. So this is screw dislocation and this is edge dislocation. So what happened is, uh, if you put a force in the direction of the Berger vector, so in edge dislocation, the direction of the Berger vector is perpendicular to edge dislocation, but the motion of the dislocation line, the motion of the dislocation line is parallel to the Berger vector, and the reverse is true for screw dislocation. The Berger vector is parallel to the screw dislocation, but the Berger vector is perpendicular to the motion of the dislocation line, the screw dislocation line, right? So in edge dislocation, Berger vector is perpendicular to edge dislocation but is parallel to the motion of the edge dislocation line, whereas Berger vector is parallel to the screw dislocation but it is perpendicular to the motion of the screw dislocation line. Now if you look at this figure, so what happens is, if you put a force in this direction, so rather than breaking all these bonds at once, what happens is that most of the force is exerted here, right? And these bonds break, right? So the edge dislocation moves along the direction of the Berger vector. So the edge dislocation has moved from here to here. With further force, the edge dislocation comes out at the end. So not all bonds are broken at the same time. Only these set of bonds are broken at a time, and then it moves gradually. So that's why the strength, the theoretical strength is actually 10 times the uh, actual strength, right? Why? Because in theoretical strength, we assume that all these bonds must be broken at the same time, whereas in actual, not all these bonds breaks at the same time, only one set of bond breaks at a time, right? First this will break, then this will break, then this will break, then this will break, and this. And what happens is that what happens is these two planes combine together and this becomes the extra half plane. In the next step, these two planes combine together and this becomes the extra half plane. In the next step, these two combine together to form a full plane, whereas this becomes an extra half plane, and so on and so forth, and this extra half plane comes out at the end. If you look at the animation below, so this is the animation of how it is happening, you know, one step, at a time. Okay, that's why the actual strength is 10 times lower than the theoretical strength. Okay, so why do we study dislocations? So there is another concept which is useful in the motion of dislocation. We call it the plan packing, right? How closely the atomic plane is packed. So if you look at this figure, so in this figure the atoms are touching each other very closely, whereas in the figure below the atoms are not touching each other very closely. So here the motion will be smooth. the dislocation motion will be smooth because this gradient is small. The slope here is small, whereas the slope here is steep. So the dislocation motion will be difficult. So dislocation moves more smoothly in close packed planes in comparison to non-close packed planes, right? So crystal structures having close packed planes will tend to be more ductile because the dislocation will can easily be moved around, whereas the crystal structures in which there are close packed planes, the material will tend to be brittle because the dislocation won't move and the material won't deform, so it will exhibit brittle properties. So this is a packed plane, atomic arrangement of triple one close packed plane in the FCC structure. Arrows indicate three different 110 directions, right? And the figure below is the atomic arrangement of 110 plane in the BCC structure. Arrows indicate two triple one directions. So if you look at this, the dislocation can move in this direction, it can move in this direction, it can move in this direction. So they are 1, 2, 3, 4, 5, 6 directions. Whereas in BCC, the dislocation can only move along these two diagonals. So here we have 4 directions. So 6, 4, right? So more ways in FCC than BCC for a dislocation to move. So the FCC will be ductile. Dislocation can easily be moved, right? And this will tend to be brittle because the dislocation will not be able to move that easily. Okay, so these are the close packed planes available in different crystal structures in BCC. The slip plane is actually the slip system is actually a combination of, we call it slip system. Slip system. It's actually slip plane plus slip direction, right? So in BCC we have these slip planes and these slip directions in which the dislocation is more likely to move around. Whereas in FCC we have these slip planes and these directions. If you look at this, these are actually families, or these are families of planes and directions, right? Because the plane has been enclosed in braces here, so it's not only 110 plane, it is all the uh, all similar planes of this type 110, right? Planes and direction. Same FCC, triple one planes and 110 directions, and HCP and other ones. Okay, so this is how slip occurs when you put a metallic rod in under a tensile stress, right, or tensile load. Tensile load. So slip occurs along the close pack direction because the force is in this direction, but slip is occurring in this direction. Why? Because the close pack or the slip systems that got activated lies along these planes, right? So that's why you see elongation, but if you put the same rod after putting tensile load on under the microscope, you would see these kind of this kind of behavior of stretching. Okay, so the stress required to cause the dislocation to move increases exponentially with the length of the Berger vector, right? So the length of the Berger vector increases the stress required to cause the dislocation to move. Thus, the slip direction should have a small repeat distance or a higher linear density. If you go back to chapter number 3 for for what is repeat distance and what is higher linear density. The close packed directions in metals and alloys satisfy this criteria and are the usual slip directions. Okay, the stress required to cause the dislocation to move decreases exponentially with the interplanar spacing of the slip planes, right? So if the interplanar spacing between slip planes increases, the stress required to move the dislocation decreases. Slip occurs most easily between planes of atoms that are smooth and between planes that are far apart. Okay, so on this point, let me go back to this slide. If you look at these two figures, so if I draw a plane at the center of these balls, so the distance between these two planes is d, right? But if I draw a plane at the center of these, so the distance here is d. From visual inspection, you would see that, let's say if this is d1 and this is d2, d1 is greater than d2, right? So if the planes are close packed, the interplanar distance or spacing will be higher. If they are non-close packed, the interplanar distance or spacing will be small, right? So that's why the dislocation tends to move along the planes for which the interplanar spacing is high. So this is what they are saying in this point. Slip occurs most easily between planes of atom that are smooth and between planes that are far apart, which means far apart means high d, right? DHKL. Okay, planes with a high planar density fulfill this requirement. What is planar density? Planar density is the amount of atoms in the, or the number of atoms in the plane. For example, if we take this is 110 plane of BCC. If you talk about, if you draw FCC, this is 110 plane of, sorry, one, this is 100 plane, and this is also 100 plane of FCC, right? So the planar density here is 1 because there is one atom per face of the unit cell, and here this is, there are two atoms. For FCC, the planar density is 2 and here it is 1. So close packed planes have higher planar density as well. Therefore, the slip planes are typically close packed planes or those as closely packed as possible. Dislocation do not move easily in materials such as silicon or polymer which have covalent bonds. Why? Because covalent bonds are directional directional bonds. The material typically fails in brittle manner before the force becomes high enough to cause appreciable slip. Uh, if you remember, in metals there is an electron C which actually binds the atoms of the element together. So if a bond is broken from one place, it can easily be formed at another place because all the atoms are the same and there is abundant number of electrons to make the bond. Whereas in covalent bond, the bond is directional. For example, if we take an example of H2O, so there is a hydrogen and there is a hydrogen, right, on either side. So if the bond breaks here, it cannot be made, on the same side here. Why? Because the unpaired electrons, one is here and the other is here, so the bond needs to be here, right? So this is called directionality of the bond. Clear? So the material typically fails in a brittle manner before the force becomes high enough to cause appreciable slip. In many engineering polymers, dislocation play a relatively minor role in their deformation. The deformation in polymers occurs mainly as polymer chains become untangled and they are stretched, right? So mainly the deformation or the stretching that you see in polymers is not because of the motion of the dislocation, but it is because of the untangling of the polymeric chains inside the polymer, right? Because you know that polymers are made of very long chains. Okay, materials with ionic bonding, including many ceramics such as MgO, are also resistant to slip. Moment of a dislocation disrupt the charge balance around the anions and cations, requiring that bonds between anions and cations be broken. During slip, ions with a like charge must also pass close together, causing repulsion. Finally, the repeat distance along the slip direction or Berger vectors is larger than that in metals and alloys. Again, brittle failure of ceramic materials typically occur owing to the presence of flaws such as small holes before the applied level of stress is sufficient to cause dislocation to move. It is possible to obtain some ductility in certain ceramic using special processing technique. So if you look at this example, dislocation in ceramic material, we're going to explain the last point of the previous slide. A sketch of a dislocation in magnesium oxide, which has the sodium chloride crystal structure and a lattice parameter of 0.396 nanometer, is shown in figure 4.9. Determine the length of the Berger vector. So here we have an edge dislocation, and if you draw the a closed loop, you are going to end up with an open loop which can be closed by a Berger vector. Now this is a 110 direction. So if this is a 110 direction, it means that this should be what? A 110 plane. Why? Because if you remember, HKL direction is perpendicular to HKL plane. Now if you put a shearing force in this direction, what will happen? If this is your A9, this is a negative charge and this is a positive charge, so what will happen? This is going to move here, right? Clear? Okay, and a negative will come near another negative ion and it will repel each other. So we are going to have a separation of the planes because of the repulsion between similar uh, charge ions, right? So that's why the dislocation cannot be easily caused to move in a ceramic material. In certain planes it can easily move around, but not in many planes. So here we are going to determine the length of the Berger vector. So the length of the Berger vector is, as I said that the plane is 110 because it's perpendicular to the direction that they have given. So we have a naught is given, so h square plus k divided by under root of h square plus k square plus l square. So the interplanar spacing is 0.280 nanometer. So this Berger vector is actually equal to the interplanar spacing of 110 plane. So note that this formula for calculating the magnitude of the Berger vector will not work for non-cubic systems. It is better to consider the magnitude of the Berger vector as equal to the repeat distance in the slip direction. So here if you look at we are doing it for copper, so copper is FCC. So this is actually, if I draw this unit cell, so it will look like this, right? So you're going to have atoms here as well. right, and here as well, right, and here as well, clear, there and there. So okay, so this is the, in this direction, 110 direction, right, 110 direction, we are going to have an atom in the middle as well, right? So the Berger vector is going to be equal to half of under root 2 a. Why? Because this diagonal, this is a and this is a, so this diagonal must be under root 2 a, because these are the latest parameters, so under root 2 a now. So because there is a atom in the middle as well, so this will be divided by 2, right? So this is, under root 2a, so you are going to have a phase angle of 0.51125 nanometer. Dividing it by 2, you will get the length of the Berger vector, right? So this is actually half of the phase diagonal. Okay, identification of preferred slip planes. Preferred slip planes means which planes the slip will occur, right, easily. So the planar density of a 112 plane in BCC iron is 9.94 multiplied 10 to the power 14 atoms per cubic centimeter. Remember, the higher the planar density, the higher the chances of dislocation to move in those planes, right? So uh, if the planar density is high, so it will be a preferred slip plane for dislocation motion. So calculate the planar density of 110 plane and the interplanar spacing of both the 112 and 110 planes, on which plane would slip normally occur. So what we are going to do is we are going to calculate the planar density for 110 plane. So if this direction is 110 direction, so these planes are 110 planes. Why? Because they are perpendicular to this direction. So we are going to find out the uh, D, right? Okay, so how do you find out D? The planar density is atoms per area, so there are uh, two atoms in the plane, and the area is under root 2, multiplied by the latest parameter. So the planar density of 110 is 1.72 multiplied times to the power 15 atoms per centimeter square, whereas the planar density of 112 has been given in the problem statement, which is 0.994 multiplied times to the power 15 atoms per cubic centimeter. The interplanar distance spacing are, for D110 it is 2.266 multiplied times to the power minus 8 centimeter. For D112 it is 1.17, right? So higher planar density is, 110, higher planar distance 110, so 110 is going to be the preferred slip plane. Okay, so observing dislocation, so you can observe it under the microscope. If you see H pits, so tiny holes created at areas where dislocation meets the surface, these are used to examine the presence and number of density of dislocation. Slip line, a visible line produced at the surface of a metallic material by the presence of several thousand dislocations. Slip band, collection of many slip lines, often easily visible. So in A, you see uh, a slip plane, right? It has been depicted here, and these are actually, when they come out to the surface, they look like H pits. Okay, these are the H pits under the microscope. And these are the dislocation pileups, right? Okay, so what is the significance of dislocation? Why do we study it? There are two type of deformation that we usually study. One is called elastic deformation, the other is called plastic deformation. So what is plastic deformation? Plastic deformation refers to irreversible deformation or change in shape that occurs when the force or stress that caused it is removed. Right? It's irreversible. And why is it irreversible? Because the dislocation moves. And when a dislocation moves, a bond is broken. And when bonds are broken, so it becomes an irreversible process. You need to give energy, or apply force on the system in order to re make that bond, right? So breaking of bond is an irreversible process. So that's why plastic deformation is irreversible. Why? Because dislocation moves, and when dislocation moves, the bonds are broken. Okay, what is elastic deformation? Deformation that is fully recovered when the stress causing it is removed. So elastic deformation occurs due to stretching of bonds. No bonds are broken, only the bond stretches, right? And when you remove the external load, the bonds retains or gets back to its normal length, and the material recovers from stretching or strain. Okay, what is dislocation density? The total length of dislocation line per cubic centimeter in a material. What is ductility? Dislocation provides ductility in metals, right? So ductility mainly comes from the dislocation motion. Okay, strengthening, interfering with the moment of dislocation. If the more easy the motion of the dislocation, the more the material is going to be ductile. So if you put hurdles in the motion of the dislocation, the material can become more strong. So we use these concepts in strengthening the material, and what we do is we interfere with the moment of dislocation to increase the strength of the material. And it also has impact on other properties. Dislocation influences electronic and optical properties of the material. For example, high dislocation density increases pure copper electrical resistivity. Okay, so we are going to study Schmidt's law in the next lecture.